switch on your mic and say yes?
Yes.
Okay, thank you. So today we are starting a new topic, and please go and do the simple exercises of the previous topic. The principle is very simple. We convert a slow varying DC voltage to a high frequency by pulse amplitude modulation. We amplify this high frequency signal using the AC amplifier, and then we demodulate. And recover the baseband signal. So that way we are able to do away with the noise due to VIO and IIO. So that's the principle behind the chopper stabilized amplifier. Now today, we're going to start a new topic, which is the log amplifiers. I think you're doing log amplifiers also in the lab, but we'll see if you are doing it the correct way once we finish today's class. So basically, a log amplifier is an amplifier whose output is shown as in equation 1 on your screen over there. So V naught is equal to some scalar K into log of V in, where K is a constant. Or we can express it in the form, an amplifier whose output is such that E to the V naught divided by K is equal to V in. That is just rearranging equation 1. Now the practical applications of these log amplifiers as follows. Number one is in analog computation. A long time ago, before the advent of digital computers, we used to use analog amplifiers. Hence, you had names like operational amplifiers. So operational amplifiers were used to perform complex differentiations, summations, divisions, etc. Of course, nowadays, we have supercomputers which can work very fast, but still analog amplifiers are still faster than the fastest digital computer. Because you put a signal at the input and you get an almost instantaneous output on the other side, unlike a digital computer whereby you have to have a program written, then the program executes you have to have a program written in the memory, and then the operating system executes that program using clock cycles of the processor. The other application, I'll just say that before the lab, which is next to the master's class, after the measurements lab, we used to have lots of analog computers over there. In fact, it was full of analog computers. They were very, very gigantic in size. But of course, they've been removed. Now, the other application is in compressors. In audio signal processing, recording studios, and public address systems, we normally use log amplifiers in the compressors. And compressors are used in recording studio to compress a signal so that it can fit the dynamic range of, say, a transmission media. It could be a recording tape. It could be a channel. It could be like for protecting public address systems. So the compressor, basically that's what happens, that if you have signals which are beyond the dynamic range of the channel that you want to transmit it through, it compresses the signal to fit that dynamic range of that particular channel. And then if you want to recover the original signal, we go to expand it on the other side. I don't know if you get that. But basically, this is what I'm saying. Maybe I can just illustrate it with just illustrate it here. Suppose the dynamic range of your channel peak to peak is that, and the signal you want to pass through the channel has got a dynamic range bigger than the channel. Then you have to squeeze the top so that it can fit the channel. So this process is known as compression. So on the other end, you expand your signal so that you get the correct ratios back. So that's another circuit, which is an opposite of a log amp, which is known as an exponential amplifier. Okay. In other language, it would be called an expander. So log amplifiers compress, exponential amplifiers expand the signal. Okay, then they also use number 3. They also use to drive display devices with the log indication. So things like our sound recording meters, which are used to find the intensity of sound. The calibration is normally in log. So for that, you use a log amplifier to give you a log display. And then finally, I've given there, I could also use for log display indicators. Now let's start with the most basic log amplifier, which is called the basic log amplifier. So this is the simple circuit of the basic log amplifier. So in this log amplifier, the input is Vs. You got an input resistance Ri, which goes to the negative terminal of an op-amp. And then we got a diode. The voltage across the diode, we normally call it V forward or Vd. Then at the output, we got a signal which we call V naught. So let's show that this circuit, this simple circuit here, known as the basic diode log amp, can perform the log operation. So we can start with the equation of the diode, or Eber-Moll's equation for the diode, which says that the IF, the forward current of the diode, is I naught into E to the V forward over neta Vt minus 1. Remember, neta is 1 for germanium, neta is 2 for silicon. And I naught is the saturation current of this diode. Now, when the diode just starts to conduct, we find that Vf over neta Vt is greater than 1. So we can approximate this first equation as IF can be approximated as I naught e to the Vf over neta Vt. Now, if we look back into the circuit, IF is the current passing through the diode. And from your theory of op-amps, Vs must be the one responsible for providing this current IF. And of course, this will only work when Vs, the top side of Vs is positive. So the current can flow through R1. And since if you're assuming an ideal op-amp, this current won't go into the op-amp. Instead, it will go through the diode and form the current IF. So we can write that IF is just Vs divided by R1. So this circuit will only work for this side positive. Sorry, why is it? And this side negative. So if you substitute this result 3 in equation 2, Then we have Vs over Ri is I naught e to the Vf divided by neta Vt. Now let's relate Vf to V naught. Now if you look at this circuit over here, Vf, the positive side of Vf is connected to the minus input of the op-amp, and the op-amp minus input behaves as a virtual earth. So the positive side of Vf is the same as connected to the minus side of the op-amp, and the same as if it's connected to the non-inverting input, because the minus side of the op-amp acts as a virtual earth. So if you look at the orientation of Vf and V naught, the positive side of V naught is connected to the minus side of the Vf, and the minus side of V naught is connected to the positive side of Vf through the virtual earth. So we can write that Vf is the same as minus V naught. So that is what we've written over. You can write over here. So relating Vf to V naught, we can write that V naught, Vf is minus V naught. So let's substitute that in equation 4. So we'll get Vs over Ri is equal to I naught e to the minus, instead of Vf, minus V naught, all divided by neta Vt. Next, let's divide right-hand side of 6 and left-hand side of 6 by I naught. So you'll get Vs over I naught, Ri is e to the minus V naught over neta Vt. Then we take logs of left-hand side and right-hand side of 7. Then you'll get log to the base e of Vs I naught Ri is equal to minus V naught over neta Vt. So I can multiply the left-hand side of 8, left-hand side and right-hand side of 8 by neta Vt and make V naught the subject. So I'll get 9. So I've just rearranged equation 8. If you rearrange it, you get minus V naught over neta Vt. And if I multiply the left-hand side by minus 1 and then neta Vt, then I'll get equation 9. So equation 9 states that V naught is minus neta Vt log to the base e Vs over I naught Ri. So we can collectively combine minus neta Vt as K1 and 1 over I naught Ri, I'll call it K2. Then I can get equation 10, which states that V naught is some K1, where K1 is a constant or a scalar, into log to the base C K2 Vs. And this is actually our equation, our general equation of our log amplifier. Now I've given some more information over here that from 10, the basic diode log amplifier function as a log amplifier as per equation 1. That was our definition of a log amplifier. However, the accuracy of this circuit depends on the relationship between Vf and If. And this is found to be less accurate as If increases. So in order to get an accurate computation, we've got to make If, the forward current passing through the diode, as small as possible. So to improve the performance of the circuit, to improve the performance, the circuit, let me just edit this. There's no correct English. The circuit must use or must must be used with small values of IF. So the next improvement of that circuit is called the basic transistor log amp. Now, what the basic transistor log amp does, it just uses a small value for the current passing through the diode. And in this case, the diode we are going to be using is the base emitter junction of a transistor. So the circuit is connected like this, and it's called the basic transistor log amp. So we can start once again to show that this circuit can perform log computation of an input voltage. Once again, the input voltage must always be positive with respect to the ground. So Vs, it will only compute the log of Vs when the top side of Vs is positive. So let's consider Ebermol's equation for transistor. So for a transistor, we can write that IE, actually normally we write it IC, but I've started with the IE. So IE, I'm reading as I naught e to the VB over neta VT minus 1. And for VB by neta greater than 1, when the transistor just starts to conduct, then we can approximate this equation to be IE is I naught e to the VB over neta VT, where for the transistor, IE is approximately equal to IE. So we can write that from equation 2 that IC is just equal to I naught e to the VBE by neta VT. In fact, that's how Ebermol's equation is normally written. Okay, now let's find out what I1 is. I1 is the current that passes through R1 due to the source V1. The inverting input is a virtual earth. So the current is just, I1 is just Vs divided by Ri. And this current does not go through the op-amp, assuming ideal op-amp. It passes through the collector of this transistor and goes and passes through the emitter of the transistor. So we can write that I1 is just equal to Vs over R1. And if we substitute that result in equation 2 with IC is equal to IE, we get equation 5. I1 is just IC, which is IE, is I naught e to the VBE over neta VT. Now next, let's relate the VBE of the transistor to V naught. So if you look at this circuit over here, the VB of the transistor, the base is positive. For this transistor to conduct, for an NPN transistor to conduct, the base must be positive with respect to the emitter. So the emitter is connected to V naught, the base is connected to the ground. Similarly, for V naught, the positive side is connected to the emitter of the transistor. The negative side is connected to the ground. So if you relate these two, you can see that V naught is minus VBE, or VBE is minus V naught. So if you substitute those results is equation 6. VBE is minus V naught. So let's substitute this result in equation 5 for equation 5 for BVE. Instead of VBE in equation 5, you're going to put minus V naught. So you'll get 7, where I1, which is just Vs over Ri, is equal to I naught e to the minus V naught over neta Vt. Let's divide left-hand side, right-hand side of 7 by I naught. We get Vs over I naught Ri is e to the minus V naught over neta. So next we take the logs of left-hand side and right-hand side, 8. So you'll get natural log of Vs I naught Ri is equal to minus V naught. And the minus sign does not appear very clear in here. Okay, let's rearrange 9. Make V naught the subject. And let's take V naught to the left-hand side and multiply equation 9 by neta Vt. Left-hand side of 9, right-hand side of 9 by neta Vt, and make V naught the subject. And then multiply left-hand side, right-hand side by 1. So if you do that, you'll get V naught is minus neta Vt natural log Vs I naught over Ri. And if you look at equation 10, this is our standard form for our log amplifier. So if we take minus neta Vt to be our scalar K1 and 1 over I naught over Ri to the scalar K2, and we know that neta is 1 for germanium transistor, neta is 2 for silicon transistor, and Vt is Kt divided by Q, which is 0.0257, which is approximately 26 millivolts at room temperature. So you'll get V naught is minus 0.026. Here I'm assuming neta is 1 into natural log of Vs over Ri I naught. Now, if you want to compute the log in base 10, we can use this relationship that natural log of x is equal to 2.30 log to the base 10 over x. So we can convert 12 in terms of base 10, and we get V naught is equal to minus 0.026 times 2.303 log to the base 10 Vs over Ri I naught. And if you multiply this first term outside the log, you get minus 0.05986 log to the base 10 of Vs all divided by Ri I naught. Now, the important thing to note is that the output function or the output computed log is a function of I naught. If you look at equation 10 over there at the top, you see the term I naught appears over there. And I naught is actually a function of temperature. The reverse saturation current is actually a function of temperature. And I naught doubles for every 10 degrees centigrade rise in temperature. And this can lead to large errors when the temperature changes. So in order to design a good log amplifier, you got to design it so that it is independent of I naught. Now, one such design is called a matched transistor log amplifier. Now, there's also a matched transistor diode log amplifier, but I'll do the matched transistor log amplifier, which is in the notes over here. So this is the circuit of the matched transistor log amp. So in the matched transistor log amp, we are trying to get rid of the effects of the reverse saturation currents IO, which doubles with every 10 degrees centigrade rise in temperature, and will give rise to errors in the computation of our log. So if you look at this circuit keenly, if you start from the output circuit, let's using op-amp. This is a difference amplifier. In the circuit, whose output I've written as VA over here, comprising of op-amp A1. This is one log amplifier. You can see the log amplifier, the collector is of Q1 is connected to the input, the emitter is connected to the output, and the base is grounded. So this is just identical to this log amp we just studied just now. Look at this circuit over here. The collector connected to the inverting input, the base connected to the ground, the emitter, so it's just identical. So these are actually two log amps. But I'll put this square over here in Q1, 2. So these two transistors, they are fabricated in form of an IC so that their temperatures will be identical. And since they're fabricated at the same time, these transistors are actually matched transistors. There's very little difference between the two because they're fabricated at the same time and in the same silicon substrate. So they're referred to as matched transistors. The properties will almost be identical. So in effect, we got two log amps. One, the first one in the top, the input is VS1. The bottom one, the input is VS2. Remember, this will work for VS1, positive with respect to the ground, VS2, positive with respect to the ground. But when we want to compute the log, as we shall see later on, one of them, let's say like VS2, we can connect it just to a DC, a variable DC, to vary what is known as the compression ratio. How much we want to compress the signal. So let's start with the output circuit, which is very simple. Let's assume that the output of A1 is VA, output of A2 is VB. So let's analyze the output V0 as a function of VA and VB. So from your study of op-amps, this is the difference amplifier. So to analyze the difference amplifier, we can use an equivalent circuit like this. So I've just put VA over here, VB over here. This is our difference amplifier. So to analyze this circuit, we just use superposition theorem. We apply the first signal VA with the signal B is equal to 0, grounded, and then we apply signal B, we ground signal A, and then we add the two to get the total response at the output. So the output response will be summation of the two responses due to signal A, VA only, plus signal VB only. So let's consider, and we're able to do that because we are going to be operating our op-amp in its linear region. We won't be overdriving it, we'll just be operating it in its linear region. So let's consider the output of our circuit due to the signal VA only. So this is the circuit, the equivalent circuit. So I've grounded a signal VB. And if you look at this circuit, this is just our non-inverting amplifier. With an input resistance is this first resistance over here. Our feedback resistance is this AR. So The output, which I'm calling V01, which is the signal due to the first voltage VA, will just be given by V01 is equal to minus RF in general divided by RI for a difference amplifier, for an inverting amplifier, but RF is AR. This our feedback resistance is AR. Our input resistance RI is R. So we'll just get, in question 2, this R and R cancel, so you just get minus A into VA. So next, we'll consider the signal due to source VB only. So I've drawn this equivalent circuit over here. And I've considered that this VB, remember, is with respect to the ground. The signal VA replaced by its internal resistance and grounded it. Now, if I consider an imaginary voltage VP at the non-inverting input, this signal VP will be reflected at the inverting input. If I had time, I would ask your people why, if you tell me from op-amp theory, why that's the case. If I put a signal VP in my non-inverting input, this same signal will be the same as one which is reflected over here. Can somebody tell me why? From your op-amp theory that you studied in class. Continue because time is not on our side. So this signal VP at the non-inverting input will be reflected with the same signal over here. The same signal in the inverting input. And this signal will drive a current I to the ground through R. This R at the input. And this current must have come from this feedback resistance AR. So we can write that V02, the output voltage, is the drop across this R connected to the ground plus the drop across AR. So we can write V02 as VP plus I AR. So that's what I've written over, I typed over here. So V02 is VP plus I. If this point over here, the inverting input is VP, then I must be equal to VP divided by this R over here. So I'm taking a shortcut there. So question 4, V02 is VP plus I into AR, but I is VP divided by R. So I can get VP common for equation 4. V02 is VP into 1 plus AR divided by R. So the R's in equation 4. So you can get 5, which is VP into 1 plus A. Now we have to determine what is VP in this circuit. So if you look at that circuit, I thought I'd do it again. No, I did not save it. I thought I'd save it in one of my equations here. Okay, we can just go back here. So if you look at this circuit over here, what is VP? In this circuit over here, we have a potential divider formed by AR and R. So from this circuit over here, so from this, if you look at this circuit over here, the input circuit with the VP, you just get that VP is equal to VB into AR all over R plus AR. Or we can write that VP is equal to VB into AR. You can get R common in the denominator. Okay, so that's one of the results that we can get. So in my notes, I've just taken a shortcut a bit, but also you're in fifth year, you can just know this R and AR forms a series resistance. So VP would just be the ratio VB AR or divided by R plus AR, which is this form. So let's go to the notes. So we note 2 is VP plus, this was our I, into AR. And I think I've done equation 5. So here I can, from equation 4, I've taken V comma. So you take VP outside, you get 1 plus AR divided by R. And then the R's they cancel. So you get 5 VP into 1 plus A. Then we go to solve for VP, which is what I've done just now. VP is just VP into AR over R plus AR. So from the second expression in 6, all I've just done is to take R to be common in the denominator. And then I cancel the R in the numerator and denominator. Then I get VBA divided by 1 plus A. So that is our VP. Now we'll substitute it in 5. We'll substitute it in 5 over here. We've gotten what VP is in 6, this part of 6. Now substitute it over here. So if you substitute it for the VP in 5, the first expression VP, I'll use 6, the first final part of 6, which is VBA, all divided by 1 plus A. Then the next part of 5, which is 1 plus A, put it over here in the numerator. So this 1 plus A in the numerator will cancel with 1 plus A. Then all I'll get will be AVB. So V naught 2 is just AVB, which is 7. And therefore, the total response to the circuit is V naught 1 plus V naught 2. V naught 1, we got as minus A into VA. And V naught 2 is AVB. So we can get the total response as A into brackets VB minus VA. Thus we can say that the output let me see what I've written over here. I've said that the output VA in equation 8. Okay. The output VA in equation 8 is the output of the basic log comprising of the op-amp A1, whilst the correct English should have been whilst that of VB is the output of A2. So what we are going to do, basically that's what I'm saying, that in this equation 8 over here, the output to VA is the output of the log amp the log amp of the first op, comprising the first op amp, and VB is the output of the log amp comprising of the second op amp. And that's what we started with in the beginning. Remember, this was our circuit. We just gotten the output, total output as a result of VA, the input here, and VB. But VA is the output of this log ampere comprising of A1. And VB is the output of this other log amp. It comprises of A2 and transistor Q2. So now we can get the response of the whole circuit in terms of VS1 and VS2. Okay, so here I've just said that from the earlier results derived for the basic transistor log amp, we already derived the basic transistor log amp. VA is minus neta VT log to the base E, VS1 over I01 into RS, where I01 is the saturation current due to Q1. And similarly, for the second log amp, VB, its output VB is just minus neta VT log to the base E, VS2, I02, where I02 is supposed to be the reverse saturation current of the second transistor into RS. Now, let's substitute these results in 8. This is equation 8, which was giving us our total response. So if you substitute in the 8, you get a V naught total is equal to A into brackets VB minus VA. But VB is equation 10, VA is equation 9. So this is our, so from equation 11, V naught total is A into brackets, VB is this equation 10 over here, minus neta VT natural log VS2, I02 into RS. I've taken a shortcut here. That's why the minus sign is coming, the positive sign is coming, because it if you use this equation over here, equation 8, T is A into brackets VB. Okay, and VB here is this equation 10 over here. Minus VA. VA is equation 9. So this minus in 8 for VA, and there's a minus of minus theta VT, equation 9, this minus here, and this minus makes it positive. So that's why I've included it in the line at the second term here as positive. So now we just go to simplify expression 11. So we can take neta VT common. We can take neta VT common. And then whatever is in the natural log, if it is negative, we invert it. So if you do that, you'll get minus neta VT natural log. The first term is positive, which is this natural log VS1 I01. And then the second term inside the natural log is inverted, which there's a minus sign outside here. So it will be I02 RS divided by VS2. And that's how we get this. But I01 is equal to I02 because the transistors are matched. So we will be able to cancel I02 and we remain with VS1 over VS2. So I've said that from 13, if Q1 and Q2 are matched, the output is independent of the reverse saturation current I0, and hence gives better performance than the basic transistor log amp. However, the output is still dependent on VT. Remember, VT is KT divided by Q. Thus, so long as VT is constant, and the output will be correct. Now let's look at a better circuit which can do away with, no, not yet. Now let's, now this circuit over here, I don't think you're using this circuit in the lab. Excuse me. This circuit, I don't think you're using this one in the lab. This is still a very theoretical circuit. It is not a practical. The theory is good, but in practice, if you use this circuit, you want to get correct answers. The reason is that op-amps, because of the offset voltages, you have to use null offsetting circuits inside the op-amp for you to get the correct answer. And this is why I was wondering if you are getting correct results in the lab. So all these are not practical circuits you can do in the lab. Now, the practical circuit that you can do in the lab is this next circuit over here. This one, which we call the practical log amp using my transistors. Now, if you look at this circuit, it has this potentiometer P1 over here. It's going to null off. It's called a null offsetting circuit. It's connected through a high resistance to one of the terminals of the op-amp. Most of the op-amps, as I said, if you ground the two inputs, you'll find there'll still be some output voltage due to the offset voltages that appear the output of the op-amp. So this is the circuits that you should be able to do in the lab. So potentiometer P1 is used to null offset this op-amp A1, and potentiometer, this other potentiometer here, the extreme right over here of the circuit, is used to null offset. We call it null offsetting the op-amp. You go to the lab and ground the two inputs of an op-amp, put the power supply, put a voltmeter at the output, you'll be shocked at the voltage that appears at the output, even with the inputs grounded. So that's why this is called a practical logarithmic amplifier using matched transistors. Assume Q1 and Q2 are matched. Of course, in the lab, it will be difficult to get match Q1 and Q2. But if you're diligent enough, you take a sample of 10 transistors, check their HFEs, the multimeters which you can use to test the HFEs of the transistor. Now, let's see how this circuit is able to compute the log. It's not the best circuit, but it's a practical circuit. So for this, CR, you have class after this? Or we can take some 10 minutes?
We have class.
Okay, is it online or offline?
It's online.
Okay. Okay, then maybe I think I'll go to 3 minutes. So to analyze this circuit, I'll consider an arbitrary voltage V over here, just to help with my computation. The null offsetting circuit does not come into play because we use high resistance. It's just for balancing, making sure that when there's no signal at the inputs of the two op-amps, the output is 0. So I'll consider an arbitrary voltage V over here, just to help with the computation. So if you look at the output circuit alone, whose output is V0, if you got a potential V at the inverting input of A2, this potential will send a current down through R3. And that current must have come from V0 through R4. So we can write that V0 is V plus the drop across R4. R4 is this 29.5K. So we can write this equation over here. V0 is V plus the current that passes through this R4, the current that passes through, with the same current that passes through. The current that passes through R3 is V divided by R3. So the current that is through this feedback resistance R4. So V0 is V plus the drop across R4, which is the current, which is V0 by R3 into R4. Or you can rearrange it, get V outside common as 1 plus R4 by R3, or you can rearrange it in this form, make R3 common denominator, V0 is equal to R3 plus R4 over R3. Now I think I'll have to stop over there. We've got another class. We've got another class because we have to do now more. Okay, so I'll stop over there unless there's any questions. Unless there's any questions.
Yes, I have a question or a comment regarding the question you asked, why the voltage VB was reflected onto the other side. Is it because of for an ideal op-amp, the infinite resistance?
What is infinite resistance? No,
for an ideal op-amp.
No, that's not correct. Because the output voltage of an op-amp, say V0, okay, in general is given by the difference between the signal at the inverting, non-inverting input minus inverting input. Let me put it here. V0, general op-amp is given by T into, I don't know what symbol you people were taught in your year. U plus minus U minus. The difference between the two input voltages. And since the maximum voltage of a typical op-amp maybe is 15 volts, AD is typically how much? How many dB? 80 dB? 80 dB is how much? Okay, let's give a 200,000. Then this tells me the difference between the two voltages. Which is, if it's in millivolts, no, microvolts. One, two, three, four, five. So the difference between the two signals, if an op-amp is giving a very large voltage, is negligible. So I hope it's understood.
Yes.
Okay, we'll stop over there.